Everybody, welcome. Darrell Lee Berry Jr. back for another Science Hour. Got a request last week I did a little bit of relativity dealing with cosmology. We sort of jumped into it. Not that I'm an expert, but that's what my class in cosmology is covering. Hey, what's going on, the mathematician? Good to see you. Glad that you're here. I saw you here early. I appreciate it. And let me know if you have any questions on the way. I'll answer them if I can. So in my cosmology class, we dealing with some relativity, and somebody requested that we sort of go back and do some basics and build up from the basics of relativity and get to Galilean transformations and then go from there. So I figured, oh, so that sounds like a good idea. So that's what we'll do. So I basically will be using a textbook that anyone can ask online. Now, I was planning that for next week, the mathematician. The next week, I plan on doing that question. So I'll look at that question over the next week. So plan on solving it in the way we discussed, learning how to parameterize those lines. And then it should be easy once I learn how to parameterize those lines or even do an approximation. But I'll start with that question next week on the stream next week. Somebody asked beforehand to do some relativity. Oh, sure. Go ahead, mathematician. We can start with that. I'll answer if I can. And as a review, while he's typing that out, last week it was a sort of view of questions. So we talked about several topics. We addressed some combinatorics, and we'll also address an area mathematical problem that'll be scheduled for next week. Actually, I'll put the link in the Stream live chat right now, so that one has already been scheduled. I called it Map Problem Solved because my plan is by then I'll have that problem solved, and we'll start with that. Let me put the link in the chat. And if you look at the current description, you'll be able to see that. So that's the one for next week. We'll talk about the map problem that's already scheduled, and I may actually, and I guess I may call it Relativity Part 2. Or maybe I'll make a separate map problem video. So I'll see. But either way it goes, next week I'll talk about the map problem, and we'll have Part 2 of Relativity. And if you look in the description, I actually have linked the video where I did a derivation of the speed of light. So we'll talk about that a little bit when we talk about, as we talk about relativity today. And be sure to let me know if my audio is okay. I noticed last week there was some kind of static effect. I'm using a different sort of program that's making this video inset type deal work, but sometimes it tries to do some audio stuff too. But I think I got that figured out, so we'll see how that goes. Awesome. Thanks, mathematician. So I'll start with relativity. I'll be looking in the chat for the mathematician's other physics question. We'll do an aside for that whenever that question pops up. So as requested, we'll go to some basics of relativity. This is a free textbook that anybody can get by, I believe it's LibreText. What is it? Let me scroll to the front. We can confirm with the just OpenStax is what it is. So anybody can get this textbook free online at OpenStax. And basically we go into chapter 5 on relativity. And this whole chapter deals with basically the topics that we were wanting to discuss. We don't get into Galilean transformations until here. So to make sure we didn't just jump right into it, I figure we'll just start with the beginning part. And what we'll do is we'll have a nice little series that goes through all the basics of relativity building upward. And it should be a good little nutshell, at least from a undergrad's perspective. I'm taking relativity right now. This stuff is actually pretty complicated. It's a very complex notation. Usually I have to go to my professor's office hours to get clarity on what's going on. So I'm sure even in this book, it'll still be sort of the very conceptual, not all of the uh, very drastic notation that Einstein developed. That's called tensors. But what we may do is have a more advanced relativity course after this one is finished. And maybe we can talk about that sometime. I'm still learning the advanced notation as well. And I'm still looking for your other question. Well, he said a picture of the question. Okay, you can go ahead and send that question in the mathematician at that same email. I'll take a look at it. Let me pull my email up and just let me know when you send it, and I'll take a look and see if I can assist with that question. So relativity. So one interesting thing is, and we'll talk about this a little bit, the fact that when we start to approach speeds that is close to the speed of light, things are not consistent. Like distances that are measured are not the same for a person that's stationary and a person that's moving. And one of the most obvious, when I say obvious, I know a lot of people are not aware of it, but obvious in the sense that so many of us use GPS so often, pretty much I don't really go out too much. And whenever I do, usually I'm having like some kind of GPS maps program, plugged into my car on a little screen there telling me where to go. And that's done by satellites like the GPS satellites. And even though they only move like about 14,000 kilometers a second or something like that, it's not very fast relative to the speed of light. It's fast enough to where the error would accumulate if we didn't take into account relativity when calculating that stuff. So the very fact that our GPS works, it's a testament to the fact that Einstein's relativity is correct. That's what allows us to have telescopes. I mean, not telescopes, but satellites that allows us to have GPS. So basically, what we're going to do is we're going to talk about some of the concepts and dynamics that goes into allowing this to happen and where that comes from. What I'll do is just scroll through the text here, and I highlighted a few things, a few points that we'll discuss in particular, and I may write some things out and make some illustrations and draw some equations to highlight these things. So the first thing says that the kilometers an hour. Thanks, Ariel. Yes, 14,000 kilometers an hour. As far as the speeds of the satellite, yeah, that's kilometers a second. I guess that'll be approaching the speed of light or something. Okay, that sounds good, mathematician. That's what I'll do is say before the end. When we get towards the end of the hour, I'll pull it up and take a look and see if we can see how far I can get on it. So this first sentence we'll do here. And good to see you, by the way, Ariel. And thanks for that correction, by the way. The special theory of relativity was proposed in 1905 by Albert Einstein. Let me say, by the way, that Albert Einstein has done so much. Like I spoke last week about how we have this thing called Einstein solids in thermodynamics. Um, we talk about them in, it seems like almost every class I'm in now, we mention something Einstein did again. This dude figured out so much stuff. That it's amazing. He's popular for relativity. But there's so many things that I can't even think of them all. Just so often is my relativity professor said that if you're in doubt about who did something, is pretty safe bet to guess that Einstein did it or invented it. Special theory of relativity was proposed in 1905 by Albert Einstein. It describes how time, space, and physical phenomena appear in different frames of reference that are moving at constant velocity with respect to each other. So this brings up the difference between general and special relativity, which is important. So, which is a distinction that's new to me as well. So, special relativity in general. So we'll be dealing with special, which means that we're dealing with inertial reference frames. So an inertial reference frames means that everything is moving at a constant speed in relation to each other or no movement. So if I have a reference frame that I'm in, which I'll call S, and we have an object that's moving, Basically, what relativity says is we can assign another reference frame to this object. So this is the object. I'll move the velocity of it up here to make it clear. And what's going to happen is the velocity that this object experiences or is having is relative to frame S. But in the frame S prime, the object itself is stationary. But V has to be constant. So basically in special relativity, either things are not moving relative to each other, which of course is trivial as they say, or one object or frame of reference is moving at a constant velocity. And it's that constant velocity that makes it special, that makes it a unique case. We know that most things don't move at constant velocity. Like for instance, if you look at the solar system, there's the sun, and the Earth is constantly revolving around the sun, right? And we talked about satellites earlier. The satellites are constantly revolving around the Earth. All of these things are basically an acceleration. So you could say that special relativity is a very special case in which things don't accelerate at all. And we'll get into a bit more of the details of that in a bit. Yeah, Einstein is pure genius. I mean, the dude did so much. I mean, is amazing. Similar to Einstein, I mean, Newton. Newton did a whole lot as well. Calculus. I mean, calculus is in everything now. I mean, I suppose if it wasn't for him, we wouldn't have relativity because we wouldn't have calculus. And we'll talk a bit about how Einstein's equations basically go back to Newtonian anyway. So it says on this bottom sentence here, even at much lower speeds of the global positioning satellite, which requires extremely accurate time measurements to function, the different lengths of the same distance and different frames of reference are significant, as I was saying earlier. So here we go. Newtonian mechanics, which describes the motion of particles, or Maxwell's equations, which specify how the electromagnetic field behaves. Special relativity is not restricted to a particular type of phenomenon. Instead, its rules on space and time affect all fundamental physical theories. So that's the thing about special relativity. Even though it's unique to systems where objects are moving at a constant velocity relative to each other, it works for everything. So whether you have a ball that's being thrown relative to the speed of light, or whether you're measuring a magnetic field produced by a particle moving close to the speed of light, special relativity will be able to give you that answer. So it doesn't really matter what it is. I could take a break right now and take a look. Mathematician, give me one moment here. Let's see. And I'll see. Okay. This is slightly a doozy of a problem. So he's showing a problem where uh, we have this, and it's saying two thin circular discs of mass m and 4 meters having radius a and 2a respectively are rapidly fixed by a massless rod to their centers. This assembly is laid on a firm and flat structure and set rolling without slipping on the surface so that the angular speed about the axis rod is omega. The angular momentum of the entire assembly about the point 0 is L, which of the following statements are true. The center mass of the assembly rotates about x-axis with an angular speed of the magnitude of angular momentum of the center mass. All right, so I have to think about this. It's like a very interesting question. It's like it's from a textbook. So I have to think about this one. If I don't, I may come back to this one today, or I may come back to this one on a different week. I don't want to give you the incorrect answer if I don't think about it well. It looks like I haven't, like this looks like a problem I haven't really done similar to before, but I'm familiar with angular momentum. So I'll come back to it. 6 hours. Oh my gosh. This problem is from that same book. What was the title of that book again? Mathematical math problems that are impossible to solve, or math problems that are difficult to solve. What's the title of that book again? Yeah, definitely your math teacher will be better. I mean, your physics teacher will be better at physics than me, so I'm sure it'll take me more than 6 hours. So, yeah. But thanks for showing it, though. It is something to look at. I'm pretty sure I could solve that. Hardest math problems and puzzles. Yeah. I'm gonna have to get that book. I mean, it sounds like some interesting problems, and I'm sure your teacher is very amused at having these interesting problems to look at. So awesome. I'll take a look at that book, but I'll take a look at this problem another time. I'm pretty sure I won't be able to solve that at the moment. Now, oh, and actually, I'll erase this here. We talked about that a little bit. Albert Einstein pondered disagreement between predictions based on electromagnetism and on assumptions made in classical dynamics. So one of the things that was amazing to me, and I mentioned this briefly in the video where I derive the speed of light. I believe I mentioned it in that equation. My electrodynamics professor, Dr. Caceres, is a brilliant physicist and an expert in electrodynamics and electricity and magnetism. She pointed out the thing that Einstein focused on. So let's say that we have a stand here, and let's say this stand is holding a wire. So this this line going over here is an electric wire, right? And of course, it has metals in it, conductive metals in there that can conduct a current. So we can look at this in two ways, and I'll copy this down and show the discrepancy that Einstein noted that relativity solved. So let's say that if I were to take this wire and with my finger, if I was to swing it back and forth, so you imagine the wire is swinging back and forth like a swing. What ends up happening is this. Oh, and forgot one detail. It's swinging back and forth. But imagine there's a magnet right here. So there's a magnet underneath the wire, and it doesn't really matter which side is which for the moment. Let's call that side north and that side south. So that means that there's a magnetic field coming out of the positive side, coming up to where this wire is, and the magnetic field loops around. So we have that deal going on. What I'm going to do is I'm going to take this wire and we're going to swing it back and forth. So now the wire is swinging back and forth inside the magnetic field. What happens is that the charges inside the metal, inside the wire, will experience a force according to this formula. As my electrodynamics professor wisely pointed out, the charge and V cross B. So basically, there will be a force that's related to the charge of the, let's say, the electrons and the magnetic field. It'll be a right angle between those, which means that we'll end up having a current that's moving through this wire in this direction. So just by moving this wire back and forth in a magnetic field, we can cause an electric current according to this force. So basically, there will be a force pushing on the charges because of the magnetic field, because the charges are moving through the magnetic field. That's one way to look at current. Now, another way to look at current is if we were to take the wire and leave the wire still, so the wire doesn't move. But what we do is we take this magnet and now we move the magnet back and forth. So imagine I'm moving the magnet back and forth like this, the wire staying still. We still end up getting a current, but now the wire is staying still. So again, the magnet was moving back and forth. So the equation in electromagnetism to calculate this current would be the electromotive force will be the integral of the electric field dotted with the wire that the magnetic field is moving through, which will be IR, and it ends up being V. And we can solve for I, and we see that we also have a current. So both of these different scenarios outputs a current, even though in one scenario the magnet is moving, and in one scenario the wire is moving. And that was something that physicists were worried about. They didn't understand how to consolidate these two frames. Einstein looked at this, and thus he was able to develop relativity, where we can calculate both of these things in relativity at once with a tensor. So I spoke a little bit about that earlier. The tensors in electromagnetism are complicated, but a little bit less. I remember right off the top of my head, you basically have a tensor, something like bx, by, bz, bx, by, bz. You might have a zero here, ex, ez. Off the top of my head, I know I'm drawing it sloppy, but suffice it to say that you have a tensor where you have the magnetic and the electric in the same entity that we can utilize to apply different mathematical properties, and we can calculate or derive both of these equations from that single metric and consolidate both of these different scenarios. But this is one of the scenarios that Einstein noticed was a discrepancy or a seeming discrepancy in the way we understand nature, and the fact that we can get a current in scenarios where one thing is moving versus the other thing is moving. Our understanding of physics is happening by two different methods, and relativity is what consolidates that. So that's why when we look at this line right here where it says special relativity is not restricted to a particular type phenomena, instead as the rules of space and time affect all fundamental physical theories, this is what it's talking about. You can take special relativity and something that's moving in a constant velocity relative to something else, no matter what it is, and you can calculate what's going on with it. Now, the interesting thing about it is the equations in relativistic mechanics differ meaningfully from those of classical Newtonian mechanics only for objects moving at relativistic speeds, meaning that if you take the complicated relativistic equations and you calculate something that's moving very slow, like a car, it'll be a difficult calculation, but you'll get the same answer as if you just use classical dynamics. So the interesting thing is that at very low speeds, relativity and Newtonian mechanics agrees. And that's one of the, you could say, tenets of science, in that if we have something that's very established and works, we can't come up with something else that just, you know, does not take into account what we know works, right? So if relativity was able to calculate one thing here but was absolutely wrong over there, when we know we can calculate that with Newtonian mechanics, it will be a problem. But the fact that Einsteinian special relativity can, for instance, calculate the proper way that we need to calculate time and distance for, let's say, a satellite that's moving at 14,000 kilometers an hour, as our arrow clarified, and we can calculate accurately that. We can calculate accurately the precession of the uh, orbit of Mercury. And at the same time, we can calculate accurately, a car moving through a normal, uh, you know, moving down a street. All of those things we can calculate properly with relativity. It's just that relativity can be used to calculate slow moving things, but Newtonian mechanics cannot be used to calculate fast moving things. So Newtonian mechanics, you can say, is the limit. So basically, we had our sort of wave here. I guess one thing you can say is relativity is here, and we could say Newtonian mechanics is a subset of that, where relativity can calculate Newtonian mechanics, but Newtonian mechanics can't calculate relativity. And general relativity is even beyond that. So special relativity, as we said, is only with things that are in inertial reference frames that are moving at constant velocity. But general relativity, it has things even that's in non-inertial reference frames. So if you have something that's speeding up or slowing down at relativistic speeds, general relativity will be able to deal with that. Special relativity can only do constant speeds. So basically, general can do acceleration. Special relativity only constant speeds, and Newtonian mechanics only at the macros. I guess you could say non-relativistic speeds. All right. So that's the distinction there. If we reasonably assume that the laws of electrodynamics are the same in both frames of reference, then the predicted speed of light in a vacuum in both frames should be c. Now, this goes back to something I'm not going to go into detail here because I went into a lot of detail uh, uh, in uh, in the previous video. If you go to the description, also mathematician, go ahead and put your question here or in the chat or send it in the email. I'll take a look at it. Maybe it's something I could jump into briefly. So what you can do is go to the description and you'll be able to see that I linked a video where I go into detail deriving this, and we can see how the speed of light outputs from our understanding of electromagnetic waves, or you could even say the inherent properties of electromagnetic waves outputs the speed of light. So it's not an accident that the speed of light is what it is. It's determined by nature. And basically these are the these little, if you look at the C here, it has this basically. So in the textbook, it has these symbols. One is called the permittivity of free space, which is magnetic, which is basically how magnetic fields can, you could say the difficulty that magnetic fields have moving through a vacuum. And the other one is the permittivity of free space, which is basically electric, right? So basically this is henries per meters and farads per meters. So these inherent properties that basically outputs the limits that these fields have that are moving through space is what determines the speed of light. And we'll go to that video that's linked in the description. I call it like derivation of the speed of light, and you can see the details of that, where that comes from. But all of these things are related. To reconcile difficulties of this kind, Einstein constructed the special theory of relativity. Right? So we'll see a few more of these, and we'll end on this example here. So we'll get to this point for about a few more pages, but we need to make sure we have this background when we get into, in the future, we'll start doing more equation type stuff, but make sure you understand what we're doing here so you can follow along with that. So I plan on keeping this series going. We'll just do relativity 1, relativity 2, relativity 3. And then, as we get to the more advanced stuff, I'll just refer people back to the previous videos because I think I'll make sure to cover everything in enough detail here, where the background will be here in the previous videos. Right? And we discussed this, the term special has to do with the inertial reference frame. So Einstein's first postulate, the first postulate of relativity, make sure I'm in the right one. The postulate 1 is that the laws of physics are the same in all inertial reference frames. Right? So it says many types of waves were known, and before I'll move from that. So basically, the idea is that if we go back to this illustration here, this frame here can be called a reference frame, in which it can look at other objects and from its perspective measure its speed, right? Inertial, because we're only looking at, for instance, the speed of this object as being constant relative to that frame. So the idea is that as long as this frame here is moving at a constant speed, F equals ma will work in this frame, and also F equals ma will work in this frame. So if we're on an airplane that's moving at constant speed and we throw a ball with some force, we can utilize this calculated force and acceleration to get the mass of the ball. This person standing on the ground, stationary, to throw the same ball with the same force, but they calculate the same mass. So this is what this is talking about. As long as these frames are not accelerating reference to each other, whether this one is stationary or this one is moving at a constant speed, the laws of physics will work the same. Any experiments you do on each of these reference frames will be the same, will give you the same result, as long as neither frame is accelerating relative to the other one. And mathematician sent the part H question. Let's take a look and see here. So it looks like it's a graph. Well, listen, I think this looks simple enough. Take a look at this. What I'll do, I'll finish this relativity talk to that example. And then what I'll do for the at the end of the talk at the top of the hour, I'll pull up this question and see if we can figure it out. So hold tight to the end in about 30 minutes, and I'll take a look at that with you. This seems like a reading this graph. I think we'll be able to get this worked out then. Awesome. So let's see here. Yeah. So now Einstein's second postulate, that's the first postulate. So as long as these things are moving at a constant speed relative to each other, we know that uh, the laws of Newton's laws, for instance, will all work the same in each frame within that frame. Einstein's second postulate: many types of waves were known and all traveled in some medium. Scientists therefore assumed that some medium carried light even in a vacuum, and that light travels at speed c relative to that medium. The speed of light measured on Earth should have been c plus v when Earth's motion was opposite to the medium's flow, and c minus v when Earth was moving in the same direction as the medium. So basically, what they were saying was, for postulate 2, people believe that there must be some medium, just like how sound moves through the air, so that if the Earth is moving around the sun, let's say in that direction, and there's this medium that is going through, if the medium is going in this direction and we're moving in that direction, then basically we would have to take the speed of light and subtract Earth's motion to get the accurate speed of light. And if Earth was on the other side of the sun over here, moving in this direction relative to the medium, then basically we should have a sped up measurement of light because we're moving opposite the direction that the medium is moving. So it was Michelson and Morley experiment that came along and demonstrated that the speed of light in a vacuum is independent of the motion of the Earth around the sun, which means that if we're moving at, say, half the speed of light and we pass a star, the light from the star will still reach us at the speed of light. It won't be at the speed of light. So that was pretty interesting. Everyone observes light to move at speed c regardless of how they move relative to the light source or to one another. It might seem odd, by the way. Sounds good, the mathematician? And it might seem odd, by the way, how that can happen. And I suppose the intricacies of it still escapes me as well, but I can let you know the generalities of what happens. So if you're at so let's say you have a spaceship and you're moving away from the star at some fraction of the speed of light, let's say 0.8 c. The light from the star, when it hits you, it'll still be going at the speed of light. But let's say if that light was emitted from the star at a purple wavelength, when you see it, you'll see, let's say, a green wavelength of light that's moving at c, at c, right? So the purple light will be moving at c. The green light will be moving at c. So what's basically happening is your movement is basically taking these waves of purple light and stretching it out so that your experience of the light, the wavelengths are longer, but it's still moving at the speed of light. So that's basically in a nutshell of how we're able to recognize that light is moving at the same speed, but there's been a a relative change in direction because the light is red shifted or blue shifted. Like, for instance, the Andromeda galaxy is moving towards us or us towards it, if you want to look at it. So light from the Andromeda galaxy is blue shifted, meaning that, if the light comes out green from the Andromeda galaxy, then when we see it, it's squinched. And let's say we see it as blue. It's still moving at the speed of light, but it's squinched together so the color is a bit higher. So basically that's what happens. As you move away from a light source, you still receive it at the speed of light, but the wavelength is stretched. And it is basically a lower frequency of color. And the same thing happens if you're moving towards a light source. The wavelengths are scrunched, and you still receive it at the speed of c, but the frequency is higher, so you perceive it as a higher energy light source. It's quite interesting. Maxwell's equations are correct. Newton's addition of velocities is not correct. Is not correct for light. Not until 1905, when Einstein published his first paper on special relativity, was the correct accepted conclusion reached, based mostly on his analysis that the laws of electricity and magnetism would not allow another speed for light, as we saw earlier, because the square root of those two, permittivity and permeability, would outpush the speed of light, is inherent in the nature of electromagnetic waves. And only slightly aware of Vickers and Morley, Einstein detailed his second postulate: light travels in a vacuum with the same speed c in any direction in all inertial reference frames. So that's our postulate 2. And I'll be building upon this same file as we go along with this. So postulate 2, C is the same in all inertial reference frames. All right. Loss of agreement on the time between events, the variation of distance with speed, and the realization that matter and energy be converted into one another. These things came from that. So now we understand why we can have different measurements of time for the same event, depending on how long moving and where we're measuring it, because the speed of light is constant. And we'll talk about that in a bit. So the next section, 5.2, relativity and simultaneity. Carefully considering just how time is measured, however, shows that elapsed time does depend on the relative motion of an observer with respect to the process being measured. He measured the distance from when he saw the pulses originate, finds them equal, and concludes that the pulses were emitted simultaneously. However, because of a observer's motion, the pulse from the right, the rail car, from the direction the car is moving, reaches her before the pulse from the left and shows as shown in time frame B. She also measures the distance from within her frame of reference, finds them equal, and concludes that the pulses were not emitted simultaneously. So let me draw out what this is talking about. And we can see it here, but I'll actually talk about it a bit as we go through it. It's talking about this illustration. So basically the idea is like I believe they call it a light. Oh, you're welcome, sweetheart. Awesome. You're welcome. Awesome. So let's say that we're taking forget what a light clock is what it's called. We're not going to get specifically into a light clock. We might get into it later. But this is basically a very rudimentary discussion of a light clock, right? So what they're saying is that we have a light here. This light is going to flash, and we have a light here. This light is going to flash. And what we're going to do is we're going to take this distance. Let's say that this distance is L. This is L over 2. And I'm going to have a receptor here. Doesn't matter whether it's a person or an object, but there's a receptor here that can detect when these lights hit, right? And what we'll do is I'm going to call this frame S prime. So I've gotten in the habit of calling my prime frame the moving frame. So I try to always do things the same way. I was very confused when I took my modern physics class. Why one frame is called S and one is called S prime, and you're doing the equations, and it's easy to mix this stuff up. So throughout this whole series, if I call something S prime, we know that means that's the frame that's moving. If I call something S, we know that's the frame that's relatively stationary, that we consider stationary in our calculations. The fact is we can't really define a stationary frame because it could always be another frame that we're moving against. We could look at the sun and say the sun is stationary, but we know the whole solar system is moving through the galaxy. And we could say the galaxy is stationary, but we know the galaxy is moving through the universe, and so on and so forth. There's always another frame. But suffice it to say that relative to, let's say, an observer standing on the side of the road, I'll call this frame S, and we will say this person is going to be our relative stationary point. And therefore, according to the S frame, this train, let's say, is moving at velocity v. So let's say that this is a train that's moving at velocity v, going in that direction. And that's our S prime frame moving at velocity v relative to the S frame. And Sudhara says, if you got to send transcript of the kinematics section of the electrodynamics paper, no idea if it'd have helped you, but happy to send in case you need it. Please send it. Yeah. So definitely that'll help. Anything will help. So I'm really just beginning. I'm about to graduate in a few months, but then I'm going to graduate school. So it's going to be, all of this stuff at the next level. Ironically, you end up taking these courses again and again, but you realize that, the physics you took in high school was very watered down to get you into it. And then when you get into college, the undergraduate the lower undergraduate even is a bit watered down. And then you get to upper graduate, undergraduate, and is a bit more complex. And then you get to the graduate level where you're getting into more and more complexities where you're taking into account more and more detail. Oh yes, right now I'm studying I'm studying a bachelor's in physics and astronomy, so I'm a double major. Provided I pass my current classes, I'm in my last classes now, which it looks like I will pass at this point. I'll have a bachelor's in astronomy and a bachelor's in physics, and I'll be going for my PhD starting in the fall. And it looks like I'll be getting in the physics program. Different schools are different. Some of them actually have an astronomy degree, but some of them have a physics degree where you make your focus astronomy. But I'll be getting a physics degree and making my focus astronomy as far as the ones I'm accepted to now. So that's the plan. Now let's say that we measure this light, right? What's going to happen is when this light is emitted, is moving at c, speed of light. When this light is emitted, is moving at c. But keep in mind that this rail car is moving, so it's going to run into these lights in the front before the ones in the back had a chance to reach it. So let me say that again. This train is moving. When this light is emitted, keep in mind that light moves at the same speed no matter what. So it's not like if we're in a train and we throw up a ball, right? And as long as the train is moving at a constant pace, the ball just falls back in your hand because you're moving at, let's say 100 miles per hour. The ball is moving at 100 miles per hour. You throw the ball up and it's still moving at 100 miles per hour. You catch it in your hand. Everything is moving at the same speed. Nothing happens. But light is different. The train is moving at whatever speed. Once the light beams, it's moving at c, right? This light on the right is moving at c. This light on the left is moving at c. Both of them are moving at c. It's just that on the right side here, because it's moving in that direction, you can say this distance over here is b is less than L over 2. Because by the time the light reaches it, the receptors move there, and we can say the distance here is b is greater than L over 2. Because by the time the light catches up with the object, it has moved a bit. Even though the speed of light is very fast, it is constant. It's going to take a little bit longer for light to catch up with the object on the left side versus the right side. Now, what this means is that the receptor will measure that these two lights did not go off simultaneously. The receptor will measure the front half first, and then afterwards, because the speed of light is fast, we can't go that fast. So eventually the light from the left will catch up with us. And when it does, we'll think that it went second. So what this means that in this scenario, with the receptor moving to the right, the receptor will measure the light on the right is going first, and the light on the light on the left is going second. Now, if we compare this to the stationary frame S, remember in the stationary frame, this frame is, we're going to consider this our stationary frame. Again, there's no all objective stationary frame, but we're going to say that this is our stationary frame in the sense that we're measuring the speed of the train relative to this frame. And what the person on the ground is going to see, if we were to flash the light at the precise moment when the observer and the receptor are right in front of each other, the receptor, the observer in frame S is going to see the light go off here and the light go off there. The light is going to have the same amount of distance to reach this receptor. And this person is going to say that they went off simultaneously. The distance that they traveled here, we'll call this, maybe I'll call this, I'll just call this S. Let's call it DS, let's say. So DS over here equals DS over there, right? And, you know, we can say that this will be DS equals the square root of L over 2 squared plus, and we should call this D squared. So this distance DS will be the same on both sides for the observer, and they went off at the moment they were in alignment, and this person is going to say they went off at the same time. What special relativity says is that both of these observers are correct. The person on the train is correct. The light on the right did go off before the light on the left. They were not simultaneous. But the person on the ground is correct. The lights did go off simultaneously, and now it depends on which frame you're in, whether they were simultaneous or not. And this is how, depending on your reference frame, the time frames of things can be different. And it gets even more crazy by the fact that even the distances of things can be different, depending on your reference frame. Right, so this is basically how far I wanted to get today. And to review what we did, we covered the difference between general and special relativity, the fact that special relativity deals with inertial reference frames in which the objects are moving at a constant velocity relative to each other. General relativity deals with things that are accelerating or having different rates of speed. I'm pretty sure if you do something like a black hole, like the things that's going on close to a black hole, you will need general relativity. We talked about the discrepancy that Einstein found that led him. He's one of the things that led him to special relativity. The fact that if we calculate the force on a charge that's producing a current in this wire from the wire moving back and forth in a magnetic field, we get the same current, but we move the magnet back and forth, but it takes two different equations, two totally different processes that's producing the same current. Magnetism says what gives, in a classical sense, how can these two different phenomena make the same current, but in two different ways, but it's the same way? Because, I mean, basically what's happening is from the perspective of the wire, the magnet is always moving. From the perspective of the wire, the magnet is moving. From the perspective of the magnet, the wire is moving. So both of these things are actually going on at the same time. It's just that depending on which perspective you take, you have to calculate it differently, right? In the perspective in which the magnet is still, you know, you can't, this one right here, the magnet is still, you can't use this equation because the magnetic field, the electric field is not moving. The magnet is moving. So you can't use one equation in one frame. You can only use it in the other. So that's where the discrepancy comes from. Conversely, if the wire is staying still, you have to use this equation. You can't use this equation because the charges aren't moving. The charges aren't moving relative to the magnetic field, so you can't use this equation. So depending on which reference frame you pick, one frame is totally invalidated. One equation is totally invalidated. Special relativity is what consolidates these things. And we talked a little bit about. I didn't go into detail of this, but if you look at the video in the description, I believe I went into detail of that a bit. We talked about the two first postulates. The laws of physics are the same in all inertial reference frames as long as objects are moving at a constant speed relative to each other. You throw a ball up, you put force on it, F equals ma works on a moving train as well as standing on the ground, as long as there's no change in speed, as well as the second postulate that the speed of light is the same in all reference frames, and the way it works is the wavelength of light is either stretched or squinched, depending on whether you're moving with the speed of light, with the direction of light, or against it, and it'll either be red shifted or blue shifted. It'll still reach you at C. The color will literally be different because it's moving at a different frequency. And we looked at this example of how you have an inertial frame and a two objects in an inertial frame, one moving at a steady speed and one stationary. Light will actually, in an event, the sequence of events will be different depending on your reference frame, right? In one frame, the events happen simultaneously because the lights reach you simultaneously. They have to have gone on at the same time because the distance between each of these is the same. For the person that's standing on the side, at the same time, the person on the train will measure L over 2 on both sides, but will, experience one light hitting them first. So the person on the train will say, hold up, I'm in the middle of the train. Each of these sides is L over 2. So of course the one on the light had to have went faster, went off sooner, right? But from the perspective of the light itself, the person on the train rushed to meet the light on the right side, but sped away from the light on the left side, and thus the difference in time happened. So depending on which reference frame you pick, the events didn't happen at the same time. And that's again why uh, satellites have to take into account special relativity, because things will happen. It's happening at a different time for the satellite versus on Earth. And if that's not taken into account, then our GPS will be wrong, right? So awesome. So that's what I wanted to get through with special relativity. This is the foundation of what we'll discuss in the future. So make sure you understand this. Let me know if you have any questions on it in the comments. And what we'll do is simply continue from here. Like I said, this textbook we'll get into everything we want to get into. The Galilean transformations are here, but it's going to be based upon everything we did today. So if we don't get to the Galilean transformations next time, it'll be the third time. But we went through 2 sections today. I plan on going to do 2 sessions next time: time dilation and link contraction, just to make sure we go through enough detail. And then the third week we'll start to get into Galilean transformations, and we'll actually get into these equations, and then everybody should be able to keep up with all the different equations and the stuff we'll be talking about at that time. So thank you for the suggestion, Siddharth. My pleasure to provide. And let's look at this problem that the mathematician brought up in our final moment. So give me a moment, I'll pull that up and see if I can share that on the screen so everybody can see what the problem is. One moment here. Moment here. Um, save the image and I'll put it up on the screen. Almost there. I'll get a drink while I'm doing this. So let me go back to my share screen. And I think I'm blocking my, there we go. And let me add this image into the stream here, and y'all will be able to see it. I think I'll put it there. Call this problem 1. Right, there we go. Y'all should be able to see that. Oh, the book I was using is a free book. You'll be able to get it. It's from I'll share it again real fast. It's called University Physics Volume 3. It's free online. This is actually one of the series of books. I was a learning assistant for a Physics 2 course and the electromagnetics course, and the professor used this book. I mean, he used version 2 of this book. There's like 3 volumes. Volume 2 deals with a lot of electromagnetism. University physics. I'm not sure about the MP part. Ah, okay, yeah. This is a good book. You know, my professor, my EM professor, I mean, he wasn't my professor, like I wasn't in the class, I was helping in the class, but he's my mentor actually on my research. He's very good. And he used this book. It was a good book. So that's the one that we'll use to go through relativity. Make sure everybody's clear on it. All right, so let's look at this. Let's see what this problem is talking about here. So we have a uh, behavior of accumulation function. It says let, and I'll write out what we have here. So when anybody have a problem you want me to cover, just bring it, let me know. I'm gonna look at it on screen. Problem 1. It says let b of x equal integral x a f t dt with the graph of f shown above and a is constant. Find the x values of g regarding each of the following conditions. If g of 2 equals -2, what is the maximum value of g on the integral 0 to 8? So g of x is the integral of f of t. That's the graph of f on the right. So that means that f of t is a derivative. So basically, g prime should be f of t. and g prime should be the slope. So if the slope is -2, what is the maximum value of g on the interview 0 to 8? That tells me the maximum value is 2. Just looking at this tells me that h is 2. I'm looking at this properly. There's a slope on the, so basically the slope is 0 from x equals 0 to 2, and the slope is negative from x equals 2 to 6. The slope is positive from x equals 6 to 7, and the slope is negative from x equals 7 to 8. So looking at this, g of 2 equals -2. I give the maximum value of f. Right, if not 2, let's see what y'all say. Oh, sorry. Let me move this so y'all can see my screen. Sorry about that. So what I was saying was, if I'm looking at this correctly, it's saying g of x is the integral of that. So if I take the g prime, it should give me f of t, or f of g, the integral of 1 is the derivative of the other, basically. So if I take the derivative of g, that should give me f. But it tells me g is a slope. That's my first thing I wanted to look at, was thinking that g is simply the negative slope of this f function. So if I look at it that way, then basically the graph looks like this from 0 to 2. I would say g equals 0. It's saying at 2 is -2. So there is a negative slope right there. It's saying from 0 to 8. And actually, hold up, I apologize. Looks like it'll be 0. G prime is 0 from 0 to 2. And G prime is negative from 2 to 6. So it seems like the maximum value of G is 0 in the bracket from 0 to 8, because the slope of the F line is 0 there. So G is 0 there, so the maximum value is 0. And right here, G is -2. Here, G will probably be +2 if the slope is the same. G equals, hold up. I forgot that this is between 7 and 8. So it helps to write this out. This is actually between 6 and 7. So that is within the realm of 0 to 8. Actually, it'll be +2. This is 6, this is 7. Then it goes back down to 8, -2. So from 0 to 8, the full realm, I would say it'd be +2. G of 6 is +2. G of 7, say it's +2. So G of 6 through 7 is +2, given their slope. That's right. So what this is telling me is that the derivative of G will be f of x, because basically what you're doing is you have an integral on this side and a regular function on the left. So an integral is basically the opposite of a derivative. So if I was to take the derivative of both sides, what it'll do is it'll give me a derivative on the left and it'll give me a regular function on the right. So looking at this, this is telling me that the derivative of g is f, or the integral of f is g. And we see that here, the integral of f is g. That all mean that the derivative of g is f. We can actually test this out. Let's say we have an equation x squared, right? We have an equation x squared. And if I'm going to take, and let's call this h of x equals x squared. So h prime, the derivative of x, will be 2x. Now let's say and take the integral of h prime of x. That's going to be the integral of 2x dx. So it's going to be 2x to the 2 divided by 2. And so that's going to be x squared. So we can see that the derivative of one is the integral of the other. It goes back and forth. So, and this is where I get this from. So basically in this example, basically they're calling, they're just saying that this is g of x, and they're saying integral of f of x. And it's the same exact scenario. So, and the derivative of x squared gave me the derivative of g of x. You see, it's the same exact scenario. So that's the first thing I noticed. So looking at that, when I look at it from the perspective of g is the slope, g is the slope, and you notice I have to write the whole thing out to make sure I didn't miss anything. Initially, I was cutting off the graph too early, but actually the graph goes from t equals 0 here, to t equals 2 here, t equals 6 right here, t equals 7, and t equals 8. So if this is correct, that the derivative of g is f, and the derivative of f is a slope, then what this is saying is that g is the slope of the original function. So looking at it that way, I would say the slope is 0 because this is flat. So g of 0 is 0. G of 2 is 0, right? Well, depending on which side you look at. Also, you could say, I mean, this boundary condition is a bit confusing. I was always confused about boundary conditions. You could say basically a little bit to the left of this, g of 2 is 0. And a little bit to the right of this, g of 2 is -2, considering that the slope of this line is -2. So that means that t equals 5, g of uh, 5 equals -2. You could say between g of 6 and g of 7, using that same uh, slope and looking at this, it looks like it's the same exact angle. We can say that g of 6 to g of 7 is +2. So that means since the slope here is 2, that means the maximum value of g is in between t equals 6 and t equals 7 at 2. And then it goes back to g is -2 from 7 to 8. So that's why I'm seeing this. Right? So that's my final verdict on that. So you can look up the solution, let me know if I was correct. That's how I would do that problem. If I was taking this exam right now and I had to put my answer in, that's the answer I would put. And I would say the maximum value of g on that interval is 2. It's +2. And it's between the t values of 6 and 7. Certainly. So let's try to look at it in a bit more detail. And really, I would say the key to understanding this problem is really about understanding integrals and understanding the relationship between a graph and slope. So what I'll do is I'll explain it a different way, and then you will have a second way of looking at it, right? And that might help it be clear. And you could always go back to the video and see both ways of looking at it. So we're going to look at this totally different way. We're going to say that let's look at it this way. I'm going to call this X. I'm going to call this Y. And what I'm going to do is I'm going to graph, let's say, f of x equals negative x squared, and let's say, let's just say negative x squared. Good enough. Or actually, let's make it a little bit more complicated. Let's say x cubed. Let's say f of x is x cubed. And if I remember right, this graph should look something like this. I may have to look it up. I haven't drawn an x cubed graph in a while, but let's say it looks like that. Y'all can look up. The graph might be slightly. I might have my direction of my axes uh, a bit differently. Now, the way you would look at this graph is f of x is just a graph. Oh, sorry, I keep doing that. Here we go. All right, so this is our matter of fact. I can just move the problem, and we'll talk about the concept. Actually, it's not a problem keeping it on the side, right? Well, this is our graph. F of x is x cubed. Now, one thing to keep in mind is that if you have a graph, it's going to have a slope at every single point. And I think this is the key towards understanding this problem and understanding why the answer is 2. This graph is going to have a slope, meaning that at every point of this graph is going to have an angle at which it's pointing. So if we look here, the slope is going to be a line tangent to the graph. So here we can say that the slope is positive because if I was to go along this graph from left to right, I'm going upward. And let's say that right exactly here, if you look at this, right, we see that the graph is going upward here. It's like it's curving, it's going upward, but it's curving downward like this. And here the graph is curving upward like this. So there must be a point in the middle within which it turns. So at this point, slope would end up being 0. At this point right here, the slope would be 0 because it's turning from a downward pointing to an upward pointing. And here the slope is going up again. So what that means is automatically, without doing any calculations, you know that the slope of this graph from negative x to 0 is going to be positive. The slope of this graph at 0 is going to be 0. And the slope of this graph from 0 to x is going to also be positive, which means that f of x is going to be positive on the left side. F of x is going to be 0 at x equals 0. And f of x is going to be positive again at x greater than 0. You see how that goes? So let's look at another graph. Let's say I have the graph of x squared, which was what I was going to do initially, but it might make it clearer. This is my x-axis. This is my y-axis. And if I draw, let's say, negative x squared, this will maybe make it a bit more clear, right? So now I have f of x equals negative x squared. So what's going on is, at this point of the graph, I'll call this A. So why don't you let me know, the mathematician? What would you say the slope is here? Is it positive or negative? And I'll label these. So I have A, I have B, and I have C. Oh. So what would you say the slope at A is? Positive, negative, or 0? That is correct. You got it exactly right. A is positive, B is 0, and C is negative. And this is the foundation of understanding that problem. So if I was to tell you that at A, the slope is 3, is positive 3. And we can see that this graph is basically symmetric. If I was to ask you what's the slope of the graph at C, you know it's going to be negative 3. And that's all that question asked was. It told you at D equals 2, the slope is negative 2. Now again, here the slope is 0. It gets odd at the the what do you call it, the inflection points. But since it said it's negative 2, that tells me that it's talking about the right side of this thing. So I know that this slope is going to be negative because we know that if the slope is 0, it's going to be flat, right? So that's how I knew it's talking about the right side. This thing looks symmetric. So I know that when it goes back up here, this is going to be positive. And since this is symmetric, just like how if it's 3 plus here, is going to be 3 minus there, it told me it's negative 2 here, so it's going to have to be plus 2 there. And then when I look at the range of that slope is from 6 to 7, that's how I know that the value is going to be plus 2 for the maximum of the slope, which is g, because g is the derivative of f, which goes back to this integral thing. So now you have two different ways of looking at it. And between those two ways, you should be able to understand that problem, and you'll be able to address any problem you get like that. So awesome. Thanks for bringing that problem to Mathematician. Thanks for everybody who watched. And what I'll do, I'll be back next week. I'll work on the problem you gave me, the more difficult one, with the area. So it seems to me like just a matter of remembering to parameterize that line. You're certainly welcome. And I should have that answer for next week. And also we'll continue some more relativity. So be ready for some more relativity. If you want to get the book and get ahead, you can do that. And we'll continue going through until we get through some Galilean transformations, and eventually we'll get to Lorentz transformations, which I believe they're different. Because I remember the Galilean transformations are basically just as if you're in regular space. And the Lorentz starts to bring in the Lorentz the Lorentz constant, the gamma, which is what? It's v squared over c squared. We'll get to that. So thanks for everybody who showed up. Good viewership today. Like, subscribe if you haven't. Let me know if you have any questions or comments. I do have tutoring available if you'll like it. And I'll see y'all next week.